Okay, Assalamualaikum warahmatullahi wabarakatuh and very good day to everyone. Welcome back to this course, BMFG1213 Engineering Materials. Okay, in previous lecture, in part 1, you already learned on the tensile strength, the ductility of the materials, and how we measure the toughness of the material, resilience, and also how to difference between true stress and true strain. And also we discuss on the heat hardening or elastic recovery after plastic deformation. Alright, in this part 2, we will discuss on the hardness properties of the materials, the types of hardness tests, the impact properties, and also we touch a bit on the design and safety factors that we need to take consideration during designing material. Alright, let us start. Alright, let us look at these hardness properties. What does it mean by hardness? How do we define a hardness? Alright, hardness is a measure of material resistance to localized plastic deformations. Okay, so permanent indenting, so plastic deformation. So let's say we have this material, okay, and then we try to apply load here at this very small location, and then the resistance of this material to plastic deformations at this pinpoint is known as hardness. Alright, so larger hardness means resistant to plastic deformation or cracking in compressions. Okay, so this hardness can be some indication for the wear properties, whereby if the hardness is higher, okay, the hardness is higher, then it's we can assume it's a better properties, better wear properties. Alright. Alright, the question is, how do we measure the hardness of the material? Okay. So we do some quantitative measurement whereby we use some special indenter with a specific dimension and also with specific amount of load. Alright, so basically we have two type of indenter. The one here is sphere type, and then we have diamond shape. Okay, this is diamond shape. Okay, let us look one by one. What is the difference? How they measure the hardness of the material. Okay, so here this is sphere shape. Normally for this sphere shape is for steel or tungsten carbide material. Okay, tungsten carbide material. Okay, so here is the or the diameter of this sphere, and then what we do is we try to give or to apply loading here. The indenter will try to penetrate into this specimen, and once we remove the load, we can have some small indents on that particular material or specimen. So these are the value of these indents. Okay, so the capital D is referring to the diameter of your indenter material, which is your sphere steel, and D, the small d, is referring to the indents that we created after we remove the load. Right. Okay, let us look at this diamond shape. So in this diamond shape, first the indenter above surface specimen. So this is the indenter, this is your specimen, and then what we trying to do is we try to give or to apply load here, specific amount of load, and then the indenter will try to penetrate, okay, try to penetrate into the specimen surface, and after we remove the indenter or after we remove the load, then it will leave some indentation here. So this is the depth of the indentation, meaning that if the depth is higher, so it means the material is more soft. Okay, soft material. If let's say it's really only a bit here, means small area here, so means that your material is quite hard. Same goes to this sphere steel indenter. If the D value is larger, means that your material is softer. Alright. Okay. Alright, so here are some of the materials starting from plastic material into diamond. We can see here diamond have a very high hardness compared to plastic, because plastic here it is material that easily to deform. It's easy to deform, right? So it cannot resist to the indenting, or it cannot resist to the plastic deformation or cracking during indentation. Alright, now let us look at the how this hardness testing is being done. Okay, this is hardness testing machine. Right, you have this area, which is the result will be appeared here. Alright, and then you have activator lever, and this is your position of your indenter. This is your indenter, either diamond shape or sphere shape. And then this is your adjusting nut. You can adjust the head of this holder. This is your holder, and this is your specimen. Say for example your specimen like something like square here. Alright, and then what happen is we will try to indent or try to do the hardness test by lowering down the activator lever, and then the indenter here will try to penetrate into this specimen. Okay, for example here, this is your specimen, right? And then this is your indenter. It's a sphere indenter, right? And then if your material is soft, means that it will penetrate deeper, okay, deeper into your material, right? So this is your D. Right, this is a softer material. If let's say your material is really hard, and what happen is the indenter only penetrate small portion of it. So this is your D. D value is lesser compared to the softer material. So this means that your material is hard. Alright. So this is basically the hardness testing machine. And now we look at the types of hardness testing that we can do based on your materials and also based on the types of indenter. Alright. So these are some of the techniques that I told you previously. We have 4 techniques, which is Brinell, Vickers, Knoop, and also Rockwell. So these 4 testing technique can be differentiated based on their indenter and also shape of indentations, and also the different formulation. Alright, and for Brinell, we have 10 mm sphere of steel or tungsten carbide. Means that the steel or tungsten carbide is the material for that sphere indenter. And for Vickers, Knoop, and Rockwell, we use a pyramid shape, pyramid indenter, okay, which is made from diamond material. Alright. So I will explain details each of the tests in our next slide. Okay, let us look at this Brinell hardness testing. Okay, as I shown in previous slide, this is the specification of this Brinell testing. So we use a sphere shape, either steel material or tungsten carbide material. So what does it mean? It means that our indenter is really hard material. Okay, because we use steel or tungsten carbide. The diameter of this indenter would be 10 am. So meaning that this D value is 10 mm, which referring to the diameter of your sphere indenter. Alright, say this is your sample, your surface of sample, and this T value is the indents that we create during the hardness testing. Okay, so represent this one. This is in the top view, and this is side view. Alright. Right. If let's say if your material is very hard, the amount of indents will be less. So it means that the D value will be less. So your material is very, very hard. If your material is soft, then the D value would be larger. Alright, so from this diameter measurement, we can generate a formulation for this HB, hardness, Brinell hardness testing. So B is referring to the Brinell hardness testing. So here we have the load, which is referring to P, and then D basically is your 10 mm diameter, and this is your D value. Small d is referring to the indents, okay, indents diameter, which is this one. Okay, so if D value, the diameter of the indents that we created during the hardness testing, is higher, okay, means that this HB would be lower. So what does it mean? It means that our material is soft. Okay, right? So contra with if let's say the D value is smaller, so it means that our material is very, very hard. Alright, so what are the other things that we need to know when we do the hardness testing? Okay, so here we have some guidelines in choosing the load that we want to apply during the hardness testing. If let's say our material is ferrous material, what does it mean by ferrous material? Any material that consists an Fe element, right, or iron element. So we can use these 3000 kilogram as the load. Alright, and then for non-ferrous material, for example, copper, nickel, or aluminium, we can use this 500 kilogram as the load. Okay, so these are some of the example of the indenter, either 10 mm or 5 mm or even 1 mm. So you can pick or you can choose either one of these. Okay, another thing is you may correlate the Brinell hardness with the tensile strength. If you have this value of HB, you can times it with 500 to get the tensile strength of that particular material. Same goes if you want to use megapascal unit. So you just times the HB, Brinell hardness result, times with the 3.45 and you can get the tensile strength in megapascal unit. Okay, let us look at this Vickers hardness testing. What's the difference between this Vickers and also Brinell? Alright, in Vickers micro hardness, we will use diamond pyramid as its indenter. What does it mean? It means that the indenter's material will be diamond material and the shape of that indenter will be pyramid shape. Okay, what does it mean by the pyramid shape? So basically they will have these 136 degree, okay, angle, and then it will penetrate through the specimen or sample. This is your sample here, and it will indent at this amount of D value. Alright, so this is the D small value. Okay, so the indents will be created by this indenter, once you apply load here, more or less as a square in shape. So you can see here it's a square in shape. Alright, okay, means that this going in, means that the indenter is going in, and then it will create a square, okay, a square in shape, whereby we have this diagonal 2 dimensions. Say for example, this is diagonal 1 and this is this is diagonal 1 and this is diagonal number 2. So what we need to do is we make some average. Basically this D1 and D2 is close to each other, but it's different value. So what we need to do is we make some average D1 plus D2 over 2, right? Average value. Okay, from this D value, then we can plug in to this formula, which is HV. HV referring to Vickers hardness, right? So here we have the load. This is the formulation. This is the load, P referring to your load, and this is your D value. comes from this average value. Alright, so basically if your D is higher, means that, okay, your HV is lower. What does it mean? It means your material is soft, right? If let's say your D is less, reduce your D, and your HV will be higher. So it means your material is hard. Alright. So what are the other things that we need to know in this viscous hardness test? Okay, usually used on very hard material. Why we say very hard material? Because we use these diamond pyramid indenter. Diamond is very hard material. That's why we use it as an indenter. Alright, finally, one of the oldest technique. It's quite flexible, quick, and also easy to use. We call it as Rockwell Hardness Testing. Okay, what the difference between this Rockwell and others hardness testing? Let us see here. Okay, this Rockwell hardness testing use two types of indenter, which is conical shape and also sphere shape. So the material for conical shape will be the diamond material, and steel will be the material for sphere indenter. Alright, so they do not use any pyramid shape. So the difference between pyramid and also conical is the degree here. It's around 120 degrees. And this cone also produce a circular indentation, right? This is circular indentation. So in your material here, we can see the circular indentation using this diamond cone. For a pyramid shape, you can see something like this, square shape, right? This is square shape for diamond pyramid. Okay, so Rockwell will only use conical shape and also sphere shape, and this sphere still will create a circular indentation. Alright, so here are some of the scale in Rockwell. We use some scale here, Rockwell hardness scale. We use scale symbol A up to K, and it will differentiate the indenter that we use. Either it's a diamond or it's a 1/16-inch ball. Ball is referring to the steel sphere. Or is it a 1/8-inch ball? So these are the different indenter that you use based on the scale that you choose, right? And then also the load that you will apply on that hardness testing. Okay, so from 60 kilogram, it's quite high. 60 kilogram up to around 150 kilogram. Okay, so these are the Rockwell hardness scale. So make sure you use the right symbol and also the right indenter, and in the same time the right load. Okay. Alright, so this Rockwell indenter can be classified into two, basically, Rockwell B or Rockwell C. Okay, we call it Rockwell B is for ball, which is your steel sphere, and basically used for soft material. Okay, and another one is diamond cone, okay, which is for hard material, referring to the Rockwell C. So bear in mind, if your material is quite soft, and then you should use the Rockwell B type, okay, which is ball type. Okay, and then some of the parameters in Rockwell, each scale runs to 130, but only useful in the range of 20 to 100. And then minor load here, we can have 10 kilogram, and major load, which is the maximum load that can this Rockwell hardness can sustain, is around 150 for C cone. Okay. And then these are some of the figures or some of the example of the indenter. Okay, so up to now I already covered 4 of the hardness testing, which is Brinell, Vickers, Knoop, and also Rockwell. So let us see the correlation or the relationship between this hardness and also tensile strength. Okay, so these are some example comparison between a few types of hardness testing, which has we have here Noob hardness, Brunel hardness, and also Rockwell. Okay, so these are the material here. You can see the most or the highest hardness of material is nitride steel, and then the lowest one is most plastic, which is polymer material, whereby this polymer material is not really resist to plastic deformation because it's easy to deform. That's why the hardness of this most plastic is the lowest one. All right. So as I told you before, we look at this correlation between the tensile strength and also the hardness. So both tensile strength and hardness may be regarded as degree of resistance to plastic deformation, because if we recall back your stress strain curve, this is your stress and strain curve. So this basically your tensile strength, or UTS, ultimate tensile strength. So this tensile strength is basically a degree of resistance to plastic deformation. So once you exceed the limit of this UTS, so means that your material will start to necking, okay, it will deform. So both tensile and hardness is basically a degree of resistance to plastic deformation, where both hardness and tensile is proportional. Proportional. For example, here, if let's say steel in tensile strength is higher than cast iron. Okay, you can see here tensile strength for steel, okay, is higher than cast iron, and same goes as the Brinell hardness number. Okay, you can see here the Brinell hardness number here, for example, at this point, the Brinell hardness number for this cast iron also lower than the steel iron. Okay, now we go for the impact properties. Okay, what does it mean by impact properties? Okay, impact properties are related to the toughness of material. Okay, in previous lecture, if we can recall back, the toughness of metal can be measured at the stress strain curve. Stress strain curve behavior, whereby this toughness of material is the area of the materials under stress strain curve before its fracture, means that this area. Okay, what does it mean? It means that in this area the metals is able to withstand an impact. Alright, so these are the relation between the impact properties and the toughness of your material. So how do we measure the toughness of that material with this impact testing? So we use these machine, which is, we call it as impact testing machine. So these are the example. We have this pendulum that can strike to the specimen. This is your specimen. This specimen, basically this impact testing have two types. Okay, we have two types of impact testing, which is IZOT, and also another one is CHAPI. So there's two different things, IZOT and CHAPI, based on a few things. I will explain it later in next slide. And another thing, we have this, which is very, very important, is the scale, energy meter scale, whereby in this meter scale, they will show us the real value of the energy absorbed during the impact testing. Okay, it's in joule value. It's in joule units. Okay, so these are the impact testing machine. Okay, in real testing machine. Alright, so let us look at the specimen, the difference between IZOT test and also CHAPI test. What's the difference between those two testing? Okay, first we look into the specimen. Okay, first specimen. Okay, first specimen. Okay, for IZOT specimen, so this is the specimen. For IZOT specimen, the length here will be around 75 mm. Okay, Whereas for the Chappie impact test, the length here will be less, which is around 55 mm. The rest is similar. Okay, the area here 10 minus 10 mm same 10, and this is 10, and we have same thing here, V naught. We call this as V naught because it's the shape is like a V, so we call it V notch. The V notch here is a 2 mm, this is 2 mm depth, similar with the Chappie impact test, 2 mm depth. And also the other one is the angle here. The angle here is also similar, which is 45 degree. It's a standard specimen for both IZOD and Chappie impact test. It's 45 degree. Okay, so first is the specimen, and then number 2 is the strike energy absorbed, which is in IZOD test we have 167 joules, but for the Chappie we have higher position, which is 300 joule. And also another thing is the angle of striking. For IZOD test we have around 90 degrees. Okay, the angle of striking. And for the Chappie impact we have around 140 degrees to lower around 120 degrees. And another one, the test specimen is held vertically, means that, okay, this is the pendulum. Okay, this is the pendulum or the hammer. Alright, so this is your specimen. The specimen is facing, okay, the knot, means the knot here, the V knot is facing the striker. Okay, while for the Chappie test, if you see here, the knot here, the knot is facing away or opposite side of the pendulum. Okay, this is opposite side. And another thing, the displacement of this specimen is vertically. Alright, the specimen here is vertically held here. And while the Chappie impact test, the test specimen is held horizontally. Okay, so these are the difference in between IZOD test and also Chappie impact test. Okay, now let us look at the how this test is being done. Okay, alright, so this is the testing machine. So we have the scale here. This is the scale, and we have the hammer or the pendulum hammer, and this is the specimen. Okay, so this is the specimen. Okay, first, the load is applied as an impact blow from a weighted pendulum hammer that is released from the cork position at fixed height, which is H. Okay, the specimen is positioned at the base as shown. So this is the specimen. It's depend either you put either IZOD or Chappie. So based on the specimen displacement or specimen position. Alright, then you try to apply this load with this H or height. Okay, this fixed height. Okay, and then after that we release the hammer, or upon release, a knife edge mounted on the pendulum strike and fractures the specimen at the notch. Once we release this hammer, okay, this will swing to this specimen, okay, and fracture the specimen, okay, with the high velocity impact value, and then the pendulum continues its swing, rising to a maximum height, which is H prime, which is lower than H. And then after they strike and fracture the specimen, they continue swing until this H prime value. Alright, so whereby this H prime is lower than this H value. Okay, so where's the energy absorption, or where we can measure the energy absorbed? Where is the impact measurement? Okay, the energy absorption is computed from the difference between H and H prime. So it's a measure of the impact energy. Alright, so how this measurement been done? Okay, so here we have this scale. Okay, I try to make it simple. So this is your pendulum. Okay, this is your pendulum and this is your specimen. Say for example, this is your specimen here. And basically this pendulum will strike, okay, will strike to this specimen, and then they will swing up to this level. So this is your H prime, isn't it? And this will be your H. Okay, the first one will be your H, and this is your H prime. So during this first step, in this area, you have a potential. Okay, potential, which is your E is equal to mgh, right? And another part, when your once your pendulum is up to here, this H value, so another potential difference is created here. So E is equal to mgh. Alright, so where's the impact energy? The impact energy came from the difference between these two E. Alright, so we can, the energy that has been absorbed by the specimen, we can call it as kV. Okay, V notch here. So kV is equal to mg1, whereby this is 1, minus mgh2. Okay, so this will be your impact energy value. Okay, it's in joule. Alright. Okay, so I hope you understand how this testing is being done, how to measure the energy, impact energy from this testing. Alright, once you're done with the impact testing, you can see your material either showing some ductile behavior or brittle behavior. Okay, basically in brittle behavior, you will see your material will break into two pieces, right? For ductile behavior, you will see your material is having a very large plastic deformation, okay, without breaking into two pieces. Plastic deformations. Okay, so as a conclusion, if your kV value, which is your energy absorption value, is higher, means that your materials is ductile material. Okay, it's ductile material because they absorb higher energy before it fracture. Compared to your kV value is lower, it's happen to have a brittle behavior. Okay, brittle behavior. Okay. Okay, actually this impact testing is not just carried out at room temperature. It maybe can carry out at different temperature based on application of that particular material. So next slide, I will explain, or we will discuss the ductile to brittle transition temperature. Okay, DBTT, whereby this transition from ductile to brittle is happen because of the difference in temperature. Okay, now let us look at the ductile to brittle transition temperature, which is DBTT. Right, before we go detail into this phenomenon, the DBTT phenomenon, let us recall back what we have learned on the difference between brittle and ductile material. Okay, as correspond to the stress strain behavior. Okay, let's say this is stress strain behavior, stress strain graph. This is stress and this is strain. For brittle material, so we have this kind of graph. Okay, all right, and then for ductile material, so this is stress versus strain, and basically we have this kind of graph. Okay, before it fracture, this is F fracture. Okay, so the area above this line is the toughness of the material. What is the toughness of the material? It's referring to the energy absorbed, the energy that can be absorbed by the materials. All right. So if you see here, this is the energy absorbed. The amount of the energy absorbed at brittle materials is quite less, right? Compared to the ductile materials, the amount that this material absorb the energy is quite large. See? Alright. So here, what happened in brittle? There's no plastic deformation, or little or no plastic deformation. No plastic deformation. Okay. Compare with these ductile materials. This is brittle and this is ductile. Compare ductile materials. We can see here is large plastic deformation, right? Large plastic deformation. So meaning to say, in ductile material, we have large plastic deformation before its fracture. Okay, but in brittle material, we can't see, or it's very little plastic deformation, and then once it exits at this point, so it becomes fracture. So this is brittle materials. Okay, sometimes this material, a ductile material, can be brittle at a low temperature. Okay, so these ductile materials, these ductile materials can be brittle at low temperature. Okay, so there's some transition from ductile to brittle materials. So we call it as DBTT. DBTT, transition temperature. So how do this happen? Okay, how we are going to study this phenomenon? Like I mentioned previously in Charpy test, okay, this Charpy impact test is not just carried out at room temperature, but in different temperature. So in order for us to study this DBTT curve, we make some Charpy testing, right, whereby we measure the impact energy, okay, energy absorbed during impact testing times with the temperature. Okay, as similar as this graph. Okay, so from that impact testing, we will have the value of Kv, which is your energy impact, is equal to mgh1 minus mgh2. Okay, from this value, which is your impact energy value, the energy absorbed from this testing, we can plot it using this graph. Okay, so how we are going to study this phenomenon at different temperature? Okay, so let's say we do some testing in 5 or 6 samples. 6 samples. It's an identical sample. Which is 1, 2, 3, 4, 5, and 6. Say for example, this is impact testing. This is a specimen for Charpy impact. Okay, so we have 6 samples here, same material, which is identical sample, and then we do this impact testing at different temperature. Okay, say for example, this is at 40 degrees Celsius, and then we have this is at 20 degrees Celsius. So let's assume this is 1, 2, 3, 4, 5, and 6. So we plot here, somewhere here. This is maybe 1, and this is 2, and maybe this is 3, this is 4, this is number 5 sample, and this is sample number 6. Okay, so what we have here from this impact testing at 6 identical sample, we can plot the result like this. Okay, so at 40 degrees Celsius, we have this value of energy absorbed, which is around 900 joule. And then another sample, which is number 2 sample at 20 degrees Celsius, so we have a lower energy absorbed. Okay, and carry on until sample number 6, which is at lowest temperature, maybe somewhere around minus 50 degrees Celsius. So it will give you from that particular HRP impact test, it will give you around only 10 joule, okay, for the energy absorbed. So this graph is indicate the different energy absorbed at different temperature for that particular sample. Alright, so here we can see higher energy absorbed. Okay, this is higher energy absorbed. This is referring to ductile material or ductile behavior. And at this lower shelf, it will refer as brittle behavior. Why? Because we go back at this stress strain curve. If let's say brittle material, the energy absorbed, which is the area under this graph, is much lower, especially in the low temperature. And if it's ductile material, the energy absorbed here is quite large. It's much larger than this brittle material. Alright. Okay, so basically not all material have this kind of DBT curve. So next slide, I'll show you what type of material that experience this DBTT and some other materials that will not experience this DBTT curve. Alright, this is some of the material that experience this DBTT transition temperature. Okay. If you look here, this BCC, which is material with body-centered cubic crystal structure, for example, iron or plain carbon steel, show this kind of characteristic, whereby you have this ductile to brittle transition temperature. Okay, they will experience this DBTT. Okay, in the upper shelf here, this is upper shelf. In the upper shelf region, the material absorb a lot of energy and behave in a tough manner, meaning that in this area, in this upper shelf region, this material, which is your BCC metals, in this particular temperature, will show a ductile behavior, alright, because it is in a tough manner. Okay. If we look into the lower temperature, which is in this region, at the lower shelf region, only a small amount, right? Only a small amount of impact energy is absorbed. And at this particular point, the brittle fracture will occur. So this will become brittle fracture. Brittle fracture will occur. Okay, so in this area, it's a tough material and shows a ductile behavior. Alright. Okay, on the other hand, for the FCC metals, for example, copper, nickel, alright, they do not experience this DBT. Why? Because we can see here, okay, the impact energy that be absorbed by these materials is higher. Okay, if let's say the impact energy higher, means that it's experience the ductile behavior. Okay, so this is the impact energy versus temperature, and also we can see here the shear fracture, the percent of shear fracture. Okay, curve A represent the transition of temperature for a steel. So this is a steel. This is steel material. And then what does it say? In this curve A, at higher temperature, the impact energy is relatively large, correlate to a ductile mode of fracture. As I mentioned previously, at higher temperature, somewhere here, okay, at higher temperature, the impact energy is quite large. See, around 100, okay, 80 to 100 joule. Alright, so it will correlate to a ductile mode of fracture. But in the as the temperature is lower, the impact energy drops suddenly over narrow temperature range, and it will correlate to brittle fracture. It's almost similar with I previously mentioned. Alright, for curve B, it's referring to the percent of shear fracture. Okay, so you see here, this is shear fracture referring to this value. So you can see what are the percents at, for example, at 100 degrees Celsius, what are the percent of shear fractures that exist on that particular material. Okay, so 50% of fibrous fracture represent the DBTT temperature. So for example, this is 50%. Okay, you can see here, this is 50%, somewhere here. Okay, so it's a fibrous fracture. It's a form of a fracture. If we look into the morphology or the end product of the materials. And then another one is 100% of fiber fracture temperature at 110 degrees Celsius. Let's say at 110 degrees Celsius, at 110 degrees Celsius, here, somewhere here. So what happened is like 100% of fibrous fracture. Okay, so for 50 at DBT temperature, so here, somewhere here, this is the DBT temperature. So we only have 50% of fibrous fracture. Okay, let us look at the appearance or the photograph of fracture surface on A36 steel choppy V-notch. Okay, so this is the fracture surface of A36 steel choppy V-notch. As I mentioned previously, we do choppy impact test at identical sample, which is same sample, and then at different temperature to study the behavior of the DBTT, okay, ductile brittle transition temperature. So here, these are the photograph of this material, A36 steel. We do this impact choppy test at different temperatures, start from 79 degrees Celsius until below negative, which is negative 59 degrees Celsius. So what happened here, you can see that from this morphology, you can see the ductile, this is the ductile material. Okay, this is ductile. Okay, the transform into brittle fracture. Brittle fracture. Okay, so this is ductile fracture. Okay, and go to brittle fracture. For ductile fracture here, it's fibrous or dull. Okay, shear characteristic at 79 degrees Celsius. Okay, and once we lower down the temperature up to negative 59 degrees Celsius, so we can see here a very shine granular texture, which is cleavage character at this temperature. Okay, and between this, from 24 down to minus 12 degrees Celsius, we can see the difference between ductile to brittle transition. Okay, let us look at some of the failure that related to this brittle fracture problem, which relate to our DBTT problem or phenomenon, right? So in early lecture, I've given you some examples, some of the failures, which is in Liberty ship during service in World War II. This cause of failure was due to crack initiated from defects in the welded area and subjected to sub-zero temperature, because it's subjected to temperature, the different temperature. Okay, so it's related to our DBTT phenomenon. Alright, another thing is this choppy impact test, we use nitronic specimens, okay, at room temperature. This is a room temperature. This is room temperature, and this is in liquid nitrogen gas. We know that liquid nitrogen gas is very, very cool. So what happened here, because lower temperature, it shows a brittle fracture. See, the brittle fracture means it break into two pieces. If you see here, this is ductile fracture. It not break into two pieces because it have a very high plastic deformation. Alright, another famous structural catastrophic failure is Titanic vessel, Titanic hull, which happened in the year of 1912. Okay, so why this Titanic sank? Okay, why? Okay, one of the story is the hull material. Okay, one of the story is the hull material. that experience the DBTT. Okay, what we have discussed it before, which is ductile brittle transition temperature. Right, what happened that night? Okay, on the night of the Titanic disaster, the temperature is actually below the freezing temperature. Okay, that is really, really cold, below the freezing temperature, and this Titanic was actually travel at high speed. Okay, and despite of this temperature and high speeds, the hull still also contained a very high level of sulfur. Okay, the hull material, okay, this is hull material, contain this high sulfur element. So these three factors, these are some of the factors that contribute to the catastrophic failure in that hull or in that structural material. Okay, so once this hull or once this Titanic collide with the iceberg, so we have this Titanic, okay, collide with this iceberg. Say for example, this is your iceberg. So what happened actually? The hull, we expect that this hull may experience some plastic deformation. Alright, but because of these factors, it's very low temperature, high speed, and sulfur, the hull is experience a fracture, a brittle fracture without any plastic deformation. Alright, and in fact, the rough iron also fail. Okay, which referring to this theory. Okay, which is the wick of rivet. Okay, the rivet is made from the rough iron metal. Okay, so both theory is due to the brittle fracture problem. Okay, for the hull itself, it's experienced this DBTT, which is ductile brittle transition temperature, because of this low temperature. Okay, so you can see here how does this rivet contribute to the disaster, the phenomenon here, right? And we also, next slide. These are some illustration of this hull vessel. What happened during on that night? Okay. Alright, I think this is the end of the DBTT subtopic. Next slide, we will discuss on the design and safety factor, which is our limits. Okay, the limits of the safe deformation. So we will take the design factors, how much design factors, and also how much the factors of safety that we will take into consideration during design process. Alright, so design and safety factor. So as I mentioned previously, what are the limits? Okay, we want to identify the limits of safe deformation. Okay, in stress strain curve here, okay, this is stress strain curve. We already discussed this kind of graph. Okay, this is UTS, which is ultimate tensile strength, which referring to your tensile strength, and this is your fracture. Once the load is exceeding this UTS, then you will experience a necking here. Alright. Okay, for practical engineering design, the yield strength is usually the important parameter. Because why? Because this yield point, the stress yield, okay, the yield strength is determine whether your materials is experience the plastic deformations or not. Okay, the plastic deformations. Okay, so here the design stress, which is stress D, is equal to N prime sigma C, where sigma C, the maximum anticipated stresses, and N prime is the design factor, which is larger than 1. Okay, so we want to make sure, okay, this is the keyword, or this is the relation between the stress design, sigma D, and the yield strength, sigma Y. So we want to make sure that this stress design, sigma D, is less than sigma Y. So our material to make sure our material will not will not experience the plastic deformation. Alright, okay, safe or working stresses, which is referring to sigma W is equal to sigma Y, your yield strength, over N. And N is the factor of safety. Okay, factor of safety is equal or much larger than 1. Okay, let us look at the some example on this design and safety factor. Okay, so design uncertainty means we do not push the limits, right? We do not push the limit. Factor of safety, which is your end, I mentioned previously, is end, and it's between 1.2 and 4. It's standard 1.2 and 4. Okay, so this is your working stress is equal to your yield stresses divided by N. Okay, for example, okay, let us look at example. Calculate a diameter D. We want to design this kind of, for example, a wire, a cable, alright, to ensure that the yield does not occur in the 1045 carbon steel rod below. Use a safety factor of 5. Okay, what does it mean? So we have 1045 plain carbon steel. Say for example, you want to make some cable, okay, some cable. So we want to design the maximum diameter or the minimum diameter for this particular application, for this particular cable. Alright, so by considering the safety factors, which is 5, okay, they mentioned 5 safety factor. So we just use this formulation, okay, this formula. Okay, stress working is equal to stress sigma Y, which is your yield strength, over the N. N is 5. Alright, so we know that 1045 plain carbon steel, the yield stress is approximately 310 megapascal. Okay, and also the tensile strength is around 565. Okay, 565 megapascal. Okay, so we just plug in this value into this stress Y over N, and we will measure the stress working. Okay, and we know that this stress working, stress is equal to F over A naught. So our F here, this F is equivalent to this value. Okay, because we already know the load that will be applied to this particular cable is around 220,000 Newton. So we have this F value, and this A value represent our D, diameter of our cable. So when we solve this equation, then we will get D is equal 0.067 meter. So in this, based on this formulation, it will give you an idea how you are going to design your cable. What are the diameter, the minimum and maximum diameter that can this cable exceed before it fracture, or by considering the factor safety, which is your N value. Alright, next session we will discuss on the failure of materials. Alright, with this, thank you.